Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. In this and probably part of next lecture, we would look at one of the successful approximate theories for chemical bonding, and particularly for the for accounting for the pi electrons in conjugated systems. We shall look at simple aromatic and aliphatic systems, but systems with alternate single and double bonds, and how an approximation method first put forward by Professor Erich Hueckel in the early 1930s explains the basic concepts of aromaticity and the stabilization due to the delocalization of the electron cloud and so on. So, we shall look at the Hueckel's molecular orbital theory. The systems that we want to study are systems which are either acyclic, but alternate single and double bonds, this type, or ring types such as cyclobutadiene or benzene, with alternate bonds, and the whole family of aromatic hydrocarbons with naphthalene, anthracene. Of course, this is what we are used to writing, but we will see how the pi electron concept is used to understand some of the bonding, particularly the pi bonding that we see in these alternate conjugated alternate double bond single bond systems, namely conjugated systems. Of course, one would try to solve the same equation like the Schrodinger equation for such large systems, H psi is equal to E psi, but since we are looking at only the resonance energy and the concept of the pi bonds and the molecular orbitals formed from the pi bonds, we are sort of localizing our picture to the pi orbitals or the p orbitals associated with the conjugated systems. So, if we start with, for example, two carbons, of course there is no conjugation here, but there is a pi bond of course. What we can think about is the carbon with one of the p orbital plus minus and another p orbital plus minus or minus plus. We will find out that there are two possible states, and the bonding here, the pi orbital bonding, can be understood in a very simple manner by certain approximations first put forward by Hueckel. The atomic orbitals, it's essentially a linear combination of atomic orbitals approach. Okay, it's an LCAO method, and the atomic orbitals that we use for this purpose are the p orbitals. The linear combination is the appropriate linear combination, and if we involve two p orbitals, it is possible for us to get two linear combinations which are orthogonal to each other. If we use three p orbitals for a cyclic system or a linear system, then what we have is three orthogonal molecular orbitals, and likewise n atomic orbitals will give you n orthogonal molecular orbitals. Okay. So, let us start with basic picture, namely it is an approximate method. But a systematic procedure. We worry only about near neighbor interactions. That is, if we are looking at systems like this for the partial bonds, the interactions between carbons which are separated by more than one carbon in between, we do not worry about them, we neglect them, and how we do that is we will see that in the Hamiltonian matrix that we set up. We make some of the Hamiltonian matrix elements 0 and we retain only some other Hamiltonian matrix elements, and not only 1 3 but also 1 4. Either this or this, both we neglect, as well as the interactions between this carbon and this carbon, for example. Okay. So, near neighbor interactions alone are included in a suitable form, basically Hamiltonian matrix elements. Neglect overlap of atomic orbitals. Neglect. The magnitude of the overlap is sufficiently small that we do not need to consider the overlap in the calculation for the energies. If we assume that the overlap is actually 0, then there is a problem with chemical bonding, because we do think that the chemical bonding is due to the overlap between these orbitals and due to the exchange of the electron density between these different orbitals. Therefore, strictly stating that the overlap integral is assumed to be 0 is incorrect. Okay. What we say is that the overlap integrals are sufficiently small that we do not have to consider them in the calculation. Stating something is 0 is different from stating something is close to 0, and therefore we neglect. So, we have to be very careful about that here. Okay. And the rest is we will do the algebra now. Okay. So, let us start with a simple bonding system like the ethylene C double bond C, and for the time being I will not worry about the strong bond that we have. It is through the hybridization, we have already seen that. What we need to worry about, of course, there are 2 hydrogens here, 2 hydrogens here. We also neglect the influence of these hydrogens on this carbon, and what we do is to start with a p orbital on this carbon, a p orbital on this carbon. I would not write the plus minus at this point of time, but in one it's enough to identify the direction. Now, the combination that we propose for solving this system using the approximate procedure is that we write psi is equal to C1 phi P1 1, this is carbon 1 and this is carbon 2 plus C2 phi P2. Okay. So, this is the molecular orbital proposed with the coefficients C1 and C2, and we solve this equation H psi is equal to E psi. Okay. If we want to solve this as a matrix form, we have to set up the coefficient matrices, namely H11 C1 plus H12 C2 is equal to E C1, where H11 is integral phi P1, the Hamiltonian phi P1 d tau, and H12 is the integral phi P1 H phi p2 d tau. So, in general Hij will involve the phi pi and H phi pj, but here we are talking about 2 carbons, and the other equation is of course H12 C1 plus H22 C2 is equal to E C2. Okay. So, this is easily derived from whatever you have studied so far. Therefore, the Hamiltonian matrix that we are looking at is H11 minus E, H12, H12, H22 minus E times C1, C2 is 0. Okay. Now, it is also easy to see that the p orbitals associated with carbon 1 and carbon 2 are identical for that atom, and therefore, the Hamiltonian matrix element between the p orbital, the Hamiltonian and the same p orbital is going to be the same whether it is carbon 1 or carbon 2. And so, H11 and H22, which is written as phi p2 H phi p2 d tau, integral of over the coordinates of phi p2 of the electron of phi p2. If you do that, you see H11 is equal to H22. Okay. And since the Hamiltonian is Hermitian and this we are only worried about real coefficients, it is also symmetric. So, the matrix is H11 minus E, H12, H12, H11 minus E, determinant is equal to 0, which tells you that H11 minus E whole square is equal to H12 square, or E is equal to H11 plus or minus H12. Okay. What did we neglect in this here? We neglected something here. Please remember that when we did this H psi is equal to E psi C1 phi P1 plus C2 phi P2 is equal to E C1 phi P1 plus C2 phi P2. This is the equation we try to solve and get the Hamiltonian matrix. We have obviously neglected the quantities integral phi P1 phi P2 d tau, and please remember this is the overlap of the 2 p orbitals associated with the 2 carbon atoms, because they are centered on 2 different carbons. Okay. Therefore, we have inherently neglected this, otherwise what would have been our results? Our results would have been H11 minus E S11, but S11 is the normalization of the p orbital 1, so we do not need to worry about that. H12 minus E S12, H12 minus E S12, H11 minus E. This is what we should have solved, but we assumed that S12 is very, very small. Well, compared to what? Compared to all the other things which are here, H11, H12 and the energy that we are computing. So, S12 is very small, neglect. Only then we can get this energy E plus minus is equal to H11 plus or minus H12. Okay. Therefore, the difference between the 2 pi electrons in the bonding orbital, you can also say C1 is equal to C2, you will get the 2 values plus minus C1 plus minus C2, and that is dependent on which energy that you take. If you take the plus combination, you will get the plus. If you take the minus combination, you will get the minus. Okay. So, there are 2 molecular orbital wave functions, namely psi MO plus as 1 by root 2, because we are neglecting the overlap, it is phi P1 plus phi P2, and E plus is H11 plus H12, and psi MO minus is 1 by root 2 phi P1 minus phi P2, and E minus is H11 minus H12. Therefore, you see the difference between the two E's, delta E as 2 H12. Okay. The usual notation is that HII, which is 1 1 or 2 2, is denoted by alpha, and Hij is denoted by beta. Okay. Therefore, you can see that the energy is alpha plus or minus beta, and the difference between the two is 2 beta. Okay. So, this is a very simple way of doing things. You have the bonding orbital, you have the anti-bonding orbital, you have the two energies, you calculated it, and therefore, the rest of it is to find out the value of beta by substituting in the Hamiltonian for the system, what interactions that you want to keep, and the wave functions in terms of the p orbitals. Now, what about the next step? Let us take the next item, that is a slightly bigger conjugated polynuclear systems like C double bond C, single bond C, double bond C, etc. So, let us consider a simple example of a butadiene 1,3, okay, and see how we can push this idea further. Okay. Okay. Butadiene, if we are neglecting the hydrogens for the moment, and we have the 4 carbon chain, linear chain with 4 p orbitals, and call them 1, 2, 3, 4 or A, B, C, D, whatever that you wish to, and look at the H psi is equal to E psi to see what is meant by delocalization or what is meant by the stabilization due to the what you call as the homogenization of the electron cloud across the molecule. Okay. So, you have H psi is equal to E psi, psi will be a linear combination of all the 4 p orbitals. So, we can write this as C1 phi p1 plus C2 phi p2 plus C3 phi p3 plus C4 phi p4, and again because we neglect the overlaps here, there are many phi pi, phi pj, d tau is assumed to be delta ij, which is 1 if I is equal to j or 0 when I is not equal to j. So, this is approximately, this is an approximate, well, this is delta ij if I is not equal to j, but it is exactly 1 when phi p I is equal to phi pj because it is a normalized p orbital. So, given that you know that the Hamiltonian matrix is going to be immediately H11 minus E, H12, H13, H14, H22, sorry 12, H22 minus E, H23, H24, and H instead of 3 1 I will write again 1 3 because the Hamiltonian is symmetric. In this case H23 symmetric here, H33 minus E, H34, H14, H24, H34 and H44 minus E. Okay. This determinant should be 0 in order for the Hamiltonian matrix to be solved. Obviously, we have neglected Sij's. Okay. Now, the Hueckel approximation is clearly seen here as opposed to the ethylene case, the simple 2 atomic 2 carbon case, because here now we see that there are carbons which are farther away from each other, 1 3, 1 4, 2 4. If you look at these are the corresponding Hamiltonian matrix elements 1 3 here, 1 4, 2 4, and they are all also on this off diagonal. If you look at these are assumed to be again small due to the fact that the orbitals are quite far apart from each other, at least 1 carbon away from each other, and these are set to 0. Hij is set to 0 if I is equal to j plus or minus 2, not plus or minus 1. Near neighbor interactions, H12 is kept, H23 is important, H34 is important. So 1 2, 2 3, 3 4 or 2 1, 3 2, 4 3, that is important, but the farther away neighbors who are farther away are not included in the Hamiltonian matrix, and if you do that the Hamiltonian now becomes an approximate form is H11 minus E. Okay, before I write it, one more thing we need to look at. The H11 corresponds to the Hamiltonian of the molecule with the matrix element being calculated between the pi orbitals, the p orbital of this carbon C1. H22 is the Hamiltonian with the p orbitals of the carbon 2. H33 is with that of carbon 3 and that of carbon 4 for H44. Though there are 2 hydrogen atoms here and 2 hydrogen atoms here, terminal carbons do have a chemical environment slightly different from the carbons in the ring, in the chain. For the time being, we will also not worry too much about their effect, and if we neglect this terminal carbon effect, you see that the quantity that we calculate, the Hamiltonian with the p orbital for carbon 1 or the p orbital for carbon 2 or for 3 or 4, they all should be the same. Therefore, you have also this term H11, let me make sure that I do not circle it, but I highlight it, okay, H11, H11, H22, H33, H44, they are all equal, and therefore now we call that as alpha. We will erase this and set our definitions, namely HII is equal to alpha, I is equal to 1, 2, 3, 4, and let us call Hij is equal to beta if I is equal to j plus or minus 1 and is equal to 0 otherwise, that is I is j plus or minus 2 or plus or minus 3, it does not matter. Okay. Then it is easy to write the matrix as alpha minus E, beta 0 0, then this is beta alpha minus E, beta 0, this is 0, beta alpha minus E, beta and 0 0 beta alpha minus E. This should be 0, and since it is a determinant, we can probably do a simple definition, one more definition, namely x is equal to alpha minus E by beta, okay, and we will take the beta out. So if we do that, this is given by alpha minus E by beta 1 0 0 1 alpha minus E by beta 1 0 0 1 alpha minus E by beta 0 0 0, sorry, this is 1 and this is 1 alpha minus E by beta, okay, this is equal to 0. So the matrix, the determinant becomes simply x1 0 0 1 x1 0 0 1 x1 0 0 1 x is equal to 0. Okay, this is very easy to expand. Expand this, and I will not tell you what the process is. When you do the expansion, the equation that you get is x raised to 4 minus 3 x square plus 1 is equal to 0. Okay. That is the secular equation, and remember x is equal to alpha minus E by beta. So, E is here in the x. The solution of this is of course x square is minus this b square plus r minus 4ac that you can do the discriminant formula, and so the answer turns out to be 3 plus r minus root 5 by 2, and therefore x is equal to plus r minus square root of 3 plus r minus root 5 by 2. Okay. So, the answer is when you actually do the numbers, x turns out to be plus r minus 1.618 and plus r minus 0.618. So, there are 4 energies, and remember x is equal to alpha minus E by beta, and that is equal to, say, if we take one of them 1.618, then alpha minus E is 1.618 beta, or E is equal to alpha minus 1.618 beta. So, there are obviously 4 energies, namely E is equal to alpha minus 1.618 beta, alpha minus 0.618 beta, then you have alpha plus 0.618 beta, and alpha plus 1.618 beta, 4 of them, 4 energy levels. So, the quantities alpha and beta are both negative. When we calculate the integrals, are both negative. Again, recall that alpha is the wave function phi p I h phi p I d tau, and beta is phi p I h phi p I plus or minus 1 d tau. Okay. Both are negative. Therefore, if we arrange the energy levels in the increasing order, we can say, well, they are not exactly equidistant. Let's this is alpha plus 1.618 beta, this will be the lowest. The next one will be alpha plus 0.618 beta, and then the other energy will be alpha minus 0.618 beta, and this will be alpha minus 1.618 beta. Okay. So, since there are 4 electrons and we have 4 molecular orbitals, if we put the 2 electrons paired in each of them, essentially what you have is the 4 electrons having this energy. So, what is the energy therefore of the pi electron system in this case? The pi electron system in this case has 4 electrons, 2 of which have this energy alpha plus 1.618 beta, and then 2 of them have the energy alpha plus 0.618 beta, and if we neglect for the time being the pairing energy of the electron repulsion energy between the paired electrons, if we neglect that, the total energy E total is 2 times alpha plus 1.618 beta plus 2 times alpha plus 0.618 beta. Why are we worried about this? Because we want to know what is meant by delocalization and what is meant by stabilization of the electron cloud due to delocalization. To do that, the best would be to consider what is not delocalized or what is localized. So, suppose we have the butadiene as 2 ethylenic bonds, each of which CH, this as a local pi electron cloud and as a local pi electron cloud, then the energy of the system is similar to that of the ethylene. This is another ethylene if they do not interact with each other. And in the case of ethylene, we have seen that the energies are alpha plus beta for the lower energy and alpha minus beta for the higher energy, because this will be, so let me just write it in the correct order, okay, sorry. So let us write the lower energy as alpha plus beta and the higher energy as alpha minus beta. Therefore, if we had butadiene as the sum of the two ethylene systems, then there are 4 electrons, each of which will occupy an energy level with the energy alpha plus beta. Therefore, the total energy of that system will be localized 2 ethylenes would be alpha plus beta times 4 electrons, so it will give you 4 alpha plus 4 beta. Okay. However, for butadiene, we just calculated the total energy of the electrons by placing them in this order, 2 in the lowest energy level and 2 in the next higher energy level. This is what we call as the ground state for the pi electron system. Here, the total energy is 4 alpha plus 2 times 1.618 and 2 times 0.618. So, butadiene energy is 4 alpha plus 2 into 1.618 plus 0.618 beta, which turns out to be 4 alpha plus 2 times this is what, 36, 6 plus 6, 12. Oh, I do this very fast in my own language, in Tamil, so I should say local language helps here much better than adding things in a language which is not your mother tongue. Okay, is beta here. So what you have is 4 alpha, sorry, this is 1 point, so this should be 2.236. So the answer is 4 alpha plus 4 times what? 0.472, okay, 4.472 beta. Compare this with that of the ethylene. So butadiene minus ethylene, if minus 2 ethylene, sorry, minus 2 ethylene in terms of the energy, if you are looking at, the difference is 0.472 beta. Since beta is negative, you see that 0.472 times beta seems to be the stabilization energy due to the electrons being placed in these the 2 orbitals, which are obtained by the linear combination of all the 4 p electrons, the p orbitals of the 4 carbons. In ethylene, if we have to do it locally, there are 2 ethylenes, so P1 plus P2 and P3 plus P4, they would be independent of each other. So compared to that, the linear combination in which the electron cloud is sort of delocalized over all the 4 orbitals seem to give a stability of 0.472 beta, and this is what is called the resonance energy or the stabilization energy. For larger systems, stabilization energy. So Hueckel was after this to find out to what extent these systems are more stable than the sum total of the individual unsaturated systems. So here you look at it, the typical calculation of beta from numerical works appears to be minus 75 kilojoules per mole, and therefore you see that 0.472 beta is about 35 kilojoules per mole. Okay. So this is the stabilization, and now of course you can compare this with the experimentally obtained or spectroscopically obtained values, and do an iteration on this by taking better p orbitals or by taking other types of linear combinations if possible, or improving upon the Hueckel's approximation by including terms which you neglected and so on, but those are all details. What is important is that this captures the bulk of what experimentally one observes as the stabilization, and therefore this is a very successful method considering the time when this was proposed that there were no computers and almost all the molecular orbital calculations had to be done by hand, and even hand calculators were very few at the time. Therefore, this is a very, very useful method in terms of quantitatively getting the first approximate sort of values. Okay. Now, the other thing that we have to do is to find out C1, C2, C3, C4, and we see that these 4 coefficients are not necessarily all the same. You remember the Hueckel matrix. The Hueckel matrix was x1 0 0 1 x1 0 0 1 x1 0 0 1 x. It was a determinant that was set to 0, but the determinant was actually obtained by solving the matrix equation with the 4 coefficients C1, C2, C3, C4 is equal to 0, and therefore you see that the equation is x C1 plus C2 is equal to 0, which is alpha minus E by beta C1 plus C2 is equal to 0, or alpha minus E times C1 plus beta C2 is equal to 0. And likewise you write the other equations, namely 1 C1 plus x C2 plus C3 is equal to 0. That will give you the equation beta C1 plus alpha minus E C2 plus beta C3 is equal to 0. And one more equation we need, because this is linearly dependent set of coefficients, so only 3 of them need to be solved. The third equation is C2 plus x C3 plus C4 is equal to 0, which will be beta C2 plus alpha minus E C3 plus beta C4 is equal to 0. And the last, of course, you do not need it, it only verifies this, which is C3 plus x C4 is equal to 0, which is beta C3 plus alpha minus E C4 is equal to 0. Okay. So, if you solve this numerically with the energies that we have, with the energies E1 being 1 plus alpha plus 1.618 beta and alpha plus 0.618 beta and so on, there are 4 energies. If you do that, you get 4 wave functions. Namely, psi 1 is equal to 0.3717 psi P1, phi P1 plus 0.6015 phi P2 plus 0.6015 phi P3 plus 0.3717 phi P4. I believe it is normalized because you can take the squares of these and add them. I am sure you should get 1, and we have neglected the overlap between P1 and P2, P1 and P3, P1 and P4, and likewise P2 and P3, P2 and P4, and P3 and P4. Neglecting those things, you can normalize this. The second wave function, this is for, I believe, energy E1, which is E1 is alpha plus 1.618 beta. Okay. Now, for the energy E2, the second wave function, eigenfunction is 0.6015 phi P1 plus 37175 P2 minus 0.37175 P3 minus 0.6015 P4, and the energy associated with this orbital is alpha plus 0.618 beta. There are two other wave functions. Psi 3 is 0.6015 5 P1 minus 0.3717 5 P2 minus 0.3717 5 P3 plus 0.6015 5 P4, and this is associated with the energy E3 is equal to alpha minus 0.618 beta, and the last one E4, the psi 4 is 0.3717 5 P1 minus 0.6015 5 P2 plus 0.6015 5 P3 minus 0.3717 5 P4 for the energy E is equal to alpha minus 1.618 beta. Okay. So, there are 4 energy levels, and if you look at them very carefully, you would see that the orbitals, the molecular orbitals psi 1 and psi 2 are orthogonal to each other. Here orthogonality is very simple to verify because we are neglecting the overlap between orbitals which are not from the same atom. Therefore, phi P1 star, when you do psi 1 star psi 2, it is going to involve terms containing phi P1 with phi P1 star, phi P2 star, P3 star and P4 star. They are all 0 except the phi P1, and that is 1. Therefore, it is a numerical multiple of 0.3717 with 0.6015. The numerical multiple of 0.6015 with 0.3717, and 2 more multiples with of the same quantity with the minus signs, and therefore, you see that the integral psi 1 star psi 2 d tau, which is of course because it is all real psi 1 psi 2 d tau, that integral is 0. So, the orbitals are orthogonal to each other, the orbitals are normalized, and it is of course true that you can verify that psi 1 psi 3 d tau is equal to 0 is equal to psi 1 psi 4 d tau, which is also 0, which is equal to psi 2 psi 3 d tau, and is equal to psi 2 4 d tau, and is also 0 is psi 3 psi 4 d tau. So, all the 4 orbitals are orthogonal to each other, and all the 4 orbitals are normalized, and the 4 orbitals are such that 2 of them which are lower in energy, which are filled. If we go back to this picture, now let me tell you the standard terminology that people use for this is that the filled orbitals, and if you call this is the higher energy filled orbital and this is the lower energy filled orbital, the highest energy filled orbital is called in quantum chemistry highest occupied molecular orbital, and the abbreviation or the acronym is HOMO, and the lowest unoccupied, the first unoccupied orbital, the first unoccupied orbital is called the lowest unoccupied molecular orbital, and it is called LUMO, so it is called the LUMO. Okay. And the gap between the two energies, which in this case is 2 times 0.618 beta. Delta E, it is messy, but let me write that delta E is equal to twice 0.618 beta. That is called, let me go and write, there is not enough space there, let us call this as, it is called the HOMO-LUMO gap. Something that the spectroscopists can measure by proper tuning, and the frequency corresponding to the HOMO-LUMO gap is now calculated as H nu is equal to 2 times 0.618 beta in energy. Okay. So these are all things that one usually computes when one applies approximate models and one fills up the atomic orbital, the molecular orbitals to the point of having the electrons paired and then leaving the molecular orbitals which are empty and calculating the difference between the highest level and the lowest unoccupied level. And this is what it is. So let me stop at this point the version of the Hueckel theory. We have only looked at the linear system. In the next lecture, what I would do is to give you an indication of how this proceeds in general and what are the general solutions for these, and then discuss also the cyclic system where Hueckel theory was very useful in predicting the resonance stabilization energy reasonably accurately for benzene. And Erich Hueckel of course won the Nobel Prize in chemistry for his contribution to the theory of electrolytes, along with the famous theory known as the Debye-Hueckel theory. But this contribution to organic chemistry is forever remembered because of the simplicity and the physical picture that is associated with these orbitals, and the ease with which non-quantum chemists can handle molecular orbitals with simple diagrams and try and qualitatively understand the spectral features, the energetics, and the resonance energies, and so on. So it's a fundamentally important method, and what we have looked at is the first part of it, namely a few two simple systems of linear, the conjugated systems. We will generalize this result, and we will also look at the cyclic systems in the next lecture. With that, I would leave the Hueckel theory for you to look at further in the literature. Until then, thank you very much.